So this next section we're going to cover still has a connection with trig, but it also has a connection with a lot of other stuff that we've been doing. So the idea is if I have kind of a funky curve, I can't always write it as a function. So say my curve looks something like this. Here, I'm in no way going to be able to write this curve C as y is a function of x because it fails the vertical line test. So that x value has multiple y values corresponding to it. However, in a lot of cases like this, we're actually still able to write this in terms of functions, but specifically you can write the x coordinate as a function of a variable and the y coordinate as a function of a variable, and it ends up tracing out the curve. So in this case, our x can be written as what we call a function of time. So maybe this is some f of t. And then same thing, our y coordinate can be written as a different function of time, or potentially the same one, okay? So these give you a way to keep track of both your x and y coordinate, and in turn, they're both functions, which is really nice because we know functions are super important. So these specific equations, x being a function of t and y being a function of t, a lot of times I keep wanting to write y of t because that's the way we write it when we get to the calculus sequence. But each of these or this set is called parametric equations. Based on the parameter t. So t is the thing that governs both of these two coordinates, and in turn, we'll be able to plot it out. The thing about parametric equations, though, is we're not going to have arrows on the end like this. Instead, our x and y is going to be traced in a very specific orientation. So we're going to have an orientation on the curve that tells us the way it was traced out. So every single time I plug in a t value, it's going to give me a coordinate pair. So maybe when t is 0, I start here. When I increase t to 1, I move. T to 2, t to 3, t to 4, t to 5, and so on. In that case, you would trace your graph in this orientation, okay? So the resulting graph we call a plane curve. So let's go ahead. We're going to try a bunch of examples where we're given the parametric equations. We want to go ahead and graph it, and then we also want to identify it. So in the same way as our polar, when we had r as a function of theta, that we would try to eliminate those two and get it just in terms of x and y, we can really do the same thing here. We're going to be able to eliminate the t variable or whatever the parameter is to get an equation in terms of x and y. At least for some of them. We can't always do that. But the ones I specifically picked, we could do. So we are going to sketch and identify the curve, okay? So here is our x coordinate, here's our y coordinate, and I want to go ahead and graph this. Now I've gone ahead and I've picked some values of t to plug in, but usually you want some positive, some negative. Sometimes you'll be given bounds, so you're only graphing over a specific section. But here I've gone ahead and picked 5 points, and that should give us a nice idea. So if I plug in -2 for t, that would give me 1 minus positive 4. So my x value would be -3. When I plug in -2 here, -2 minus 3 gives me -5. So I'm going to go ahead and plot the points simultaneously once I get them. So when t is -2, my x value is -3, y is -5. Our starting point is down here. So I'm going to label it with my t values. When I plug in t is -1, that gives me 1 minus 1, so my x is 0. And then when I plug in -1, -1 minus 3 is -4. So that value would be right here. So t equals -1. When I plug in 0, that's nice. That gives me 1, and that gives me -3. So that value would be right here. So the thing to kind of notice, it doesn't necessarily trace this out evenly. This makes a big gap and then a small one. So your speed picks up based on the equations. When we plug in positive 1, well, that still gives me 1 minus 1 for x, so I land back at 0. 1 minus 3 is negative 2. So t equals 1 brings me back here. And then finally, when we plug in 2, that would give me 1 minus 4 for x, so negative 3. And then 2 minus 3 is negative 1. So that value would be right here. So what happens is I'm going to be coming along. I'm going to come into this point, come up, and then I've got to turn back around and go this way. Okay. So again, I don't want to trace or put arrows at the end. I want to indicate the way I graphed this. Because again, I wasn't given any values of t. I've picked it. So that means if I pick t equals negative 3, I'd start somewhere back here. So we trace our curve in this direction. Okay. So it kind of looks like a parabola. So I'm assuming my shape is going to be something involving an x squared or y squared. Since this is a sideways parabola, it's probably y squared. But what we're going to do is we're going to eliminate the parameter. So this means, again, I want to get rid of t, and I want to go ahead and figure out just an equation involving x and y. So I'm going to go ahead and rewrite our equations here. My x is 1 minus t squared. My y is t minus 3. So within these two equations, I could solve for t pretty nicely here. And then I'll go ahead and plug it into this one. So right here, we can solve for t. And then we can plug it into the other equation. So y is equal to t minus 3. Going ahead and adding 3 to the other side, y plus 3 is my parameter t. So since my x is 1 minus t squared, I'm going to go ahead and plug t as y plus 3. So my x is equal to 1 minus y plus 3 squared. And that indeed is going to be a sideways parabola. You can rearrange this if you want. But that minus tells you it's open to the left, and then these values just shift it to give you a vertex at 1, negative 3. Okay. Let's try a second example, and this one's going to involve our trig functions. But here we are going to have a restriction for our parameter. Our theta value is only going to be between negative pi and pi, so we don't go past that. So since we've got sines and cosines, it's likely going to be some kind of circle because the inside argument is the same. So I'm going to go ahead and I'm going to pick the values that are easy to evaluate this at. So we'll plug in all of those quadrantal angles between negative pi and pi. Okay. So if I start by plugging in negative pi, this would be sine of negative pi over 2. If you think about that, that's down here. The sine is the y coordinate. So these are backwards because x is dealing with sine. This x value would be negative 1. If I plug in negative pi over here, that's cosine of negative pi over 2. Again, that's on the y-axis, so the cosine is 0. So my starting point is going to be at negative 1, 0, which is back here. So this corresponds to theta equals negative pi. If I plug in pi over 2, that would give me pi over 4, and then this is negative. So negative pi over 4 is down here. That tells me my cosine is going to be positive, but my sine is negative, and I'm working with a root 2 over 2. So this one is negative root 2 over 2. This one would be positive root 2 over 2. So that would land us somewhere around here. 0 is definitely the nicest. Sine is 0, 0. Cosine of 0 is 1. So this is the point 0, 1, which is right here. And then if I plug in pi over 2, that would get me to pi over 4, which is in this quadrant. So both of these will be positive root 2 over 2, which is right here. And then when we plug in pi, this would be pi over 2, so that'll be backwards. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So that lands me right here. So this lands me on a circle, but I'm only getting the top half of my circle, and it's also traced in the opposite direction as our unit circle, okay? So I want to go ahead and I want to show that, yes, this is indeed a circle. So we need to eliminate our parameter, which in this case, that parameter is theta. So if you think about a nice connection between sine and cosine, that's our main Pythagorean identity. If I take x squared and add y squared, that would be sine squared of 1/2 theta plus cosine squared of 1/2 theta. Well, those have exactly the same angle, so that is our identity. So that right-hand side just simplifies to 1. However, I do not get the full unit circle. I am only getting the top half because we don't have the negative because of that bounds that we were given for theta. So again, this is our equation, but it is only the top half, okay? Now let's try to do the opposite. Let's go ahead and be given the normal equation, and we want to find a set of parametric equations for it. So in this first example, this one is probably the nicest that you can get. It's already a function. Y is written completely in terms of x. So in this case, one way we could parametrize this is you just let x be t. Then anywhere I see an x in this equation, you replace it by t. So your y coordinate's given by t squared plus 3t minus 4. Okay? So this would be our set of parametric equations. For this next example, that is a circle of radius 4. So we're going to utilize the same idea here, but I need to get that radius to be 4. In this case, the radius was 1. So if I want a circle of radius 4, what I'm going to need to do is I'm going to need to have a 16 on each of these after I square it. So I'm going to let x be 4 cosine of theta, and I'm going to let y be 4 sine theta. And then I'll go ahead and show that indeed this does simplify to x squared plus y squared equals 16. So if I go ahead and add these together, that gives me 4 squared cosine squared of theta plus 4 squared sine squared of theta. Well, that's 16, and then you can go ahead and factor that out. And then sine squared plus cosine squared gives us 1. So indeed, this does work. Okay. Let's try to do something a little bit different. So we're going to now find 2 different parametric equation representations for the parabola. So the first one, we're going to let x be t, and for the second one, we're going to let x be t minus 5. If x is equal to t, again, this is the simplest case because my y is equal to x plus 5 squared minus 5. So I'm just going to go ahead and replace x by t. So my y equation would be t plus 5 squared minus 5. Okay. If I need to let x be t minus 5, that one's just going to be a little bit different for y then. So in place of my x, I'm going to put t minus 5. So we'd get t minus 5 plus 5 on the inside here. And then that minus 5 plus 5 cancels. So the y coordinate would just be then t squared minus 5. Okay. So both of these are 2 different representations. They would still trace the same curve. They're just slightly different formulas for the y coordinate and the x coordinate. So the last thing we're going to talk about with parametric equations is a real life example, which is projectile motion. So if you think about throwing anything or a rocket launching or anything like that, shooting something from a slingshot, what happens is that goes up for a bit, but then it has to come back down thanks to gravity. So there are three things that are going to define this projectile motion, but they all are going to have that same shape. V0 is the initial velocity, so the strength that you throw this thing at. Theta is the angle of inclination. So that's the idea here. If you toss it up in the air, there is some theta that you throw this thing at based on that initial velocity that you shoot it off at. Okay? And then the height is just how high you throw that off the ground. So this would be our height. Every single projectile motion is going to have the same coordinates or the same formulas for our x and y coordinates. So the x coordinate is just going to be a linear function. That's going to be the initial velocity times cosine of the angle you throw it at times time, okay? So it's really just based on the horizontal component of that vector, that initial velocity you throw it at. The y coordinate is more complicated. This is where it's going to give this parabolic shape to it. So the y coordinate's given by -1/2 g t squared. Then we have v0 sine of theta t plus the height. Okay. G is just based on gravity, so it depends on the problem. If it's given in meters, gravity is 9.8 meters per second squared. And if it's in the US standard unit, that is 32 feet per second squared. Okay. So we're going to try an example of a rocket launch. We're going to come up with the parametric equations, and then we're also going to go ahead and find some key components of that launch. So let's try this example. A rocket's launched from the ground with a velocity of 52 feet per second and an angle of 60 degrees with respect to the ground. We want to figure out what are the parametric equations for the path of that rocket. So just kind of filling in what everything is. Our initial velocity is 52 feet per second. Our theta value is 60 degrees. Our height, because it's launched from the ground, is 0. And then gravity in this case, because we're given feet per second, is going to be 32 feet per second squared. Okay. So our x coordinate is given by v0 cosine of theta t. So our initial velocity is 52. Then we have cosine of 60 degrees, and that's going to be times t. Cosine of 60 degrees is a half, which is nice. So our x coordinate is really given by the formula 26t. Our y coordinate, on the other hand, gonna be much more complicated. So to rewrite that formula, that's -1/2 g t squared plus v0 sine of theta t plus h. Okay. So plugging this in, again, gravity, we're going to use the 32. Our initial velocity is 52. The angle is 60 degrees. And then the height is 0. So filling that in, that's -16t squared. Sine of 60 degrees is not pretty. That is √3/2. And so simplifying that out, 52 divided by 2 is 26. So we get 26√3t. So again, not pretty, but that is our true formula for the y coordinate. So now that we have these two equations, let's try to eliminate the parameter and find the rectangular equation that models the path of the rocket. So the easiest thing is since x is equal to 26t, we can go ahead and divide by 26. to get an equation for our parameter t. And then in here, I'm going to replace the t by x over 26. So this gives us negative 16 x over 26 squared plus 26 root 3 times x over 26. And then if you go ahead and square 26, this would give you negative 16x. And then in the bottom, 26 squared is 676. And the x should be squared as well. And then thankfully, at least here, the 26 divided by 26 cancels. And we're left with root 3x. And then you can go ahead and simplify. Both of these are divisible by 4. So this would give us negative 4 over 169x squared plus root 3x. And so this is our equation, which again is parabolic, because that is the shape a projectile has. Okay? So you can indeed use that equation to be able to answer other stuff, but a lot of times these parametric ones are much simpler to work with. So for example, if we want to figure out how long the rocket is in flight, this tells us absolutely nothing about time, where these two equations do. So if I want to know how long the rocket is in flight, I need to figure out how long does it take to hit the ground. So essentially what I'm looking for is we need to find when our y is equal to 0. Okay. So I'm going to go ahead and set that equation equal to 0. Well, that's really just a quadratic equation. And ultimately, they both have a t, so we can go ahead and factor that out. That leaves us with negative 16t plus 26 root 3 equals 0. So you set each equal to 0. Immediately, you get t equals 0. Well, that's the start, because we started at the ground. Then the other value of t is going to be when we go ahead and we hit the ground. So we need to go ahead and solve for t. So I'm going to go ahead and just add this to the other side. That gives us 26 root 3 is equal to 16t. And so dividing by 16, we get 26 root 3 over 16 is our t value. And then we definitely need this roughly as a time. I don't know how many seconds that is. This is about 2.8 seconds. Okay. The reason I know it's seconds is because, again, gravity is given in feet per second squared. So my units for time are going to be seconds. And then for this next one, we want to know the horizontal distance covered. That is going to be in feet. If you were starting out with an initial velocity in meters per second squared, your units would be meters and seconds. But if I want to know the horizontal distance that this covers, my projectile started and ended, I basically want to figure out after 2.8 seconds, what does x equal? Because we start basically at the origin. If I plug in t equals 0, the x is equal to 0. So now I'm going to plug in t is 2.8, and that gives me my horizontal distance. So we find x when the rocket hits the ground. Okay. So my x is equal to 26t. Plugging in our t value of 2.8 gives us our x is around 73 feet. So at that initial velocity, that is how far the projectile covers. Okay. So there are a lot of realistic applications to these parametric equations, and they just make life simpler. And if you're going on to calculus, in Calc 2, you go ahead and you talk about how you can apply calculus to parametric equations and talk about some of the concepts from Calc 1.